Hello, everyone, and thank you for attending this presentation on our work radio, reinforcement learning aided deployment of Wi-Fi routers in 5G networks for indoor drone orchestrating. My name is Tolga. I'm affiliated with Virginia Tech, and this has been a collaborative effort between WaveWave Incorporated, Virginia Tech, and the George Washington University. So to start off in this presentation, the agenda is first there will be a 5G overview. Then I will talk about localization fundamentals, then the design of the radio framework, and finally the evaluation. So to talk about 5G, 5G is a technology that is promising ubiquitous connectivity to a wide variety of use cases, all with different quality of service requirements. So it has very high versatility compared to its legacy variant. And in order to accommodate all these use cases at the same time, 5G offers services in the form of logically isolated network segments denoted as network slices. Right on the right here, we are seeing the depiction of these network slices, which can be classified under various umbrellas, such as enhanced mobile broadband, ultra reliable low latency communication, massive Internet of Things, and the vehicular to everything communications. And on the right here, we are seeing the coexistence of these network slices sort of come together to offer this ubiquitous connectivity to a bunch of different use cases at the same time. And in order to be able to do so, 5G has had to go through a transition from its legacy variant LTE. Right on the left here, we're seeing this legacy LTE deployment. And while the names are not important, the important thing is that this deployment used to take place over bulky proprietary servers where functions were deployed as physical network functions, right? And this led to a very monolithic service model, which is very inflexible. Now, transitioning to 5G, what we have is these network functions starting to be deployed as virtualized network functions instead of physical network functions. And now, instead of proprietary servers, they are being deployed on commercial off-the-shelf hardware. And this leads to the emergence of a microservice delivery model where we can leverage technologies, management technologies such as software-defined networking and various management orchestration units to essentially bolster our cellular deployments. And it is this transition that really enables 5G to be more flexible and to offer services in the form of network slices. So that's the 5G landscape. And now let's talk about localization fundamentals a little bit. And in the generic localization pipeline, we have three key building blocks. First, we have the signal to be measured, which can be radio frequency, acoustic, or sound. Then we have the measurement method, which can be received signal strength. It can be angle of arrival, it can be time of arrival, time difference of arrival, which are then fed into a specific localization technique, which can be based on fingerprinting, angulation, and lateration. And this will become important. I will basically summarize which specific component we choose from each building block for our design. And one other key important background information about localization is the dilution of precision or the geometric dilution of precision. And the GDOP is essentially the error in localization accuracy that results from the inaccuracies as a result of poor anchor placement. And by anchor, I mean Wi-Fi, basically any kind of transmission reception point. So on the left here, we are seeing a more favorable anchor placement, which leads to a lower GDOP. And as a result, this shaded region, yellow region, which represents GDOP, and which subsequently represents the potential error region for where this drone might be estimated to be, is much smaller. And if we look on the right, we're seeing a less favorable anchor placement, which means this region is much, much larger, which means that the drone can be estimated to be anywhere in that region. And really the goal in this particular piece of work is to understand, well, is to basically come up with a placement methodology that minimizes that region. But okay, so what is the motivation? So why do we want to do this? And to answer that, we can kind of look at this picture here that shows the flight path of a drone. And this drone, which might be a load-bearing drone, it's going from an outdoor location to an indoor location, such as a warehouse or any kind of indoor location, really. And the idea here is that we want to combine localization information from these third generation partnership project anchor points, which are outdoors, as well as non-3GPP radio access network nodes, which are indoors. And for this work, this means we want to use Wi-Fi connected to a cellular core inside, as well as cellular connection through the same core while the drone is outside. And to understand how that might look, we have kind of a sample deployment here where if we have a user that is inside the building, it will be served by the yellow highlighted non-3GPP access networks, which we have come to call these Wi-Fi G transmission reception points, as well as when it's outside, it will be served by these 3GPP access nodes, which at this point is this heterogeneous 3GPP access network. But the important thing is that the localization information from both indoor and outdoor nodes are consolidated in the same logical point in the core network, right? So this is a technology that is supported by 3GPP as in the form of interworking between cellular and other radio technologies. So before I describe the framework, I want to summarize the goals here. So our goal here is to propose this hybrid radio access technology localization framework with 5G outdoor anchors and indoor radio TRPs, right? So to centralize localization feedback for high mobility targets, we want to consolidate localization information to a common logical location in the core network. Then we want to analyze this geometric dilation of precision for this 3D space to show that these z-axis errors are more severe compared to XY plane estimations. And then our ultimate goal is to formulate and solve this optimization problem for placing these TRPs using deep reinforcement learning to optimize for both z-axis and XY plane placement. So let's talk about the actual framework. And if you remember this joint localization pipeline I showed, the specific type of components that we have chosen from these building blocks are highlighted here. So we use RF measurements based on time of arrival, and we leverage them in a lateration technique. And for this, we use trilateration, the first step of which is to calculate the distance between TRPs and users. Well, each TRP and the user. So once we have done that using simplification, it is possible to express this trilateration in matrix notation, which becomes significant which makes the computations easier when we actually we want to feed them into the DRL framework. And the DRL framework, DRL design of radio. So reinforcement learning is the type of machine learning where an agent learns to make decisions in an environment to maximize cumulative reward. Right? And the key components of this environment are, well, the environment itself, then the state, the action, and finally a reward, the reward function. So the Markov decision process for radio looks like this. First, we have the state, which is the room dimension that is fixed for a specific computation. Then we have the action, which is a vector of length 12 that represents the location of the anchors of all the basically Wi-Fi indoor nodes. And transition model, which is an action, which is that after an action is taken, the environment will transition to another room dimension if you want to make computations for different rooms. So the reward function is to basically, the goal of the reward function is to ensure that we have a low GDOP while we also make sure that the vertical and horizontal dilation of precisions, which are respectively the z-axis and xy plane estimation errors, are also kept below a specific value, a specific threshold, so as not to basically, boost the errors in a specific dimension while trying to minimize GDOP overall. And we compute this reward function over all the potential locations within the indoor space that the drone may have traversed. And the visual summary of this DRL agent is here. So we have the environment, which is the node, which is the environment within which the nodes will be deployed in. And we have a critique network as part of the PPO agent. We have one critique and an actor network. And the hyperparameters are summarized here for those who are interested. And here we have the saturation of the training process, where we can see the average return kind of get better and better over time. And the time step here is to sort of show the performance of the training process again for those who are interested. So how does this placement strategy actually work out? So how does it actually improve localization accuracy? Now, to understand this, we have two different sets of placements. First, we have the random placement pattern, where we have carried out over small, medium, and large spaces, right? So here we deploy 4 anchors, and we just randomize their deployments in these different room variants. And then we have the optimal placement, which is given here, that is obtained as a result of this radio optimization, right? And one, as you'll see in a moment, this GDOP is actually significantly improved. So how do we actually demonstrate that? So let's go over each room size one by one, right? So first we have the on the left, the suboptimal deployment. On the right, we have the optimal deployment. And as you can see, so the representation here is taking actually place in a 3D space. So to do that, for the first figure on each side is representing the XY plane estimation error. The second, which is the horizontal dilution of precision. The second figure is vertical dilution of precision. And then finally, the GDOP, which is kind of the combined both 3D error region. And as you can see, for a random placement on the left, even though we have some better accuracy in specific locations in the XY plane, that is not the case for the Z-axis, right? However, with an optimal placement, we're able to obtain very sub 5 GDOPs for the entire space, both in XY plane, Z-axis, and subsequently the entire 3D space. And if we kind of just go through all the deployments, we can see that a similar pattern emerges for the entire, for the comparison, right? So the only difference is that as the room size gets larger and larger, our final optimization kind of starts to suffer a little bit in the edges of the room. So for instance, on the right, we can see in the GDOP plot that even though we have very good accuracy in the middle of the room, towards the bottom right edge, we are able to see some deterioration. Mainly, the GDOP jumps from sub 5 to around 9 to 10. And finally, for the larger room, the same pattern continues. We are able to see that better accuracy is obtainable in the middle of the room. However, it gets progressively worse towards the edges. All right, so in conclusion, what we did here was propose this 5G localization framework using Wi-Fi for indoors. We explained the integration of Wi-Fi-based localization with the outdoor 3GPP-based localization to motivate the work. Then we constructed this core network model, which showed how consolidating localization information for different access technologies can benefit localization. And then in our evaluations, we actually developed, well, to show how indoor localization can be improved. We developed the radio framework for the optimal placement of these TRPs for indoor localization. And then we evaluated the performance using GDOP in a 3D space with separate constraints on Z-axis and XY plane estimations. Thank you for listening.